Okay, so what we're going to look at here are our domain and our range of a function here. So the domain is considered the x value, and then the range is considered the y value, and how that's kind of important to functions. But to start off, let's take a look at an example of a composition. So the first thing we want to identify is we know that g of x is this function right here. And if I slide over to the graph, you can see that f of x is this other function over here represented by a graph. Okay, so what we're going to look at here is, first of all, we need to find out that g of f of 2, that's how you say that out loud, g of f of 2. Okay, so the first thing I want to identify is, well, where is f of 2? So I'm going to go over to the f of x graph, and I'm going to see here that if I substitute in 2, the output is 2. So that's the value that I'm looking for. Okay, so f of 2 is 2. So if I rewrite this equation right now, I can say g of 2 equals. And now what I need to understand is that now I'm switching over to the g function. So g of 2 is this function up here. And I'm going to substitute in 2. So 2 times 2 squared minus 5 times 2 plus 1 equals, and you can see in my calculator I stored it 2 into x and then typed in the expression, and then I got an output of negative 1. So we can say g of f of 2 equals negative 1. Right, so there's some practice and review with some compositions here. Okay, so how does that relate to domain and range? So what we're looking at here is domain is the x values, and then the range is the y values. In this example right here, consider a function that has its inputs at this is the number of months of the year. Right, so the inputs are the number of the months of the year. Okay, so we can write them as numbers just to make this a little bit easier. So what I'm going to write here, I'm going to say let 1 equal January. And then I'm going to write this 1, 2 for February, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 is December. And if you really wanted to, you can write out the names themselves. And then we're looking at the output of this function is the number of days in each month. So the output of our function here, what we're going to write here is there's 31 possible days. There are 30 possible days. And notice we're talking about non-leap years, so we also need 28 for February. So if I were to write out this function as a set of ordered pairs, I can say the following. I can say, well, I know that January has 31 days. I know that February has 28 days. And I know that March has 30 days. And then notice that April has 31 also, and it's still a function because April always has 31 days. And then January always has 31 days. Okay. Next example, sometimes you have a relation, right? We've got a f of n here, and it's defined as 2n plus 1. So that's our definition of our relation, and it is a function. It's a linear function. So what we need to determine here is if we have the domain as the set 1, 3, and 5, what is the range going to be? So I'm going to substitute in f of 1, f of 2, and then f of 3. And that's going to give me my range. So I've got 3 here, 5 here, and 7 here. So my range of a function, 1 would go to 3, 3 would go to 5, and I'm sorry, 2, this is 3 would, wait, I did this wrong here. So this is 3, and then this is 5, 1, 3, and 5. Sorry about that. Okay, so let's go back. I was trying to rush here a little bit. Notice that you make mistakes when you rush, everybody. Okay, so I'm going to substitute 1, 3, and 5 in. Okay, so 1, 3, and then 5 in. Okay, so f of 1, f of 3, and then f of 5. So 1, 3, and then 5. So f of 1 is 3. So 1 goes to 3. So if I substitute 3 in, 2 times 3 is 6 plus 1 is 7. So 3 goes to 7. And then 5, 2 times 5 is 10 plus 1 is 11. And then I'm going to get 11 in my range. Okay? So notice the domain is the set of x values, what I'm substituting in. In this case, it's n is the independent variable. And then the y values are given in the range. Okay? Next example, how do we talk about domains and ranges? How do we express domains and ranges here? And there's two ways to do it. We can use interval notation or set notation. First of all, interval notation, hopefully you are familiar with. We've got this value right here, which means we do not include this numbers. And we've got this symbol right here, which means we do include the numbers. Think about a staple. And then we've got a union of numbers, which means or, which means this set or this set, okay? And then if you're talking about all real numbers, we want to talk about the concept of infinity. So let's see how those work in practice here. If I'm going to look at the numbers 3 through 10, and then I'm not including 3, that means I get a parentheses, and then I'm not including 10, I'm going to substitute a parentheses in here. If I want the numbers between 2 and 7, and I want to include 2, I want to put a little bracket on 2, but I don't include 7. I think of the bracket as kind of like a staple. And then if I want all numbers greater than 10, including 10, I'm going to say I want to staple 10, or I'm going to include 10. And then if I'm talking about all real numbers, I'm going to use the infinity symbol because it's just going to go on to infinity. And then you put a parentheses around infinity because infinity is infinite. It keeps going on forever. It can't ever actually equal infinity. So we use a parenthesis with infinity. Okay, so now how does this translate into set notation? So if you're a STEAM person, you should really, really have a strong kind of understanding of this set notation. How this works, you would read this as x such that all numbers between 3 and 10. So I'm going to put 3 right here, 10 right here. I'm talking about x, and I need to think about, I'm not including 3. Right? So it's all numbers greater than 3. And it stops at 10, but it doesn't include 10, so we've got to have less than 10. And then you're just going to close off your brackets. And the same thing is true for this. I'm going to say, hey, we're talking about x. So this is good for domain and range. You'll see in the next example. I'm talking about x such that I've got 2, and then I've got 7. I'm talking about x, okay? Now, I'm including 2. So we want to say less than or equal to 2. But notice that I'm not including 7, so I just have the value is less than 7, and then close it off with the brackets. Okay, so that's called set notation. So this is how the set notation works when we're talking about numbers here. And this is why set notation is nice, because you can see down here, I've already got the x values represented, and then the y values represented. Okay. So first, let's look at the x value. So if I'm looking at this graph, the farthest left that this goes on the x value is -3. And then the farthest it goes to the right is 1, 2, 3, 4, 5, 6. So we know it runs from -3 to 6, and we know it touches -3 and 6. So using set builder notation, I would say -3 is less than or equal to x, which is less than or equal to 6, because it includes both of those numbers. Now I'm switching over to the y. So remember, the y value is how low does the graph go? 1, 2, 3, 4, -5 is the lowest value, and it touches -5. And then 3 is the highest y value, and it touches 3. So I'd write it like that using interval notation. So using set builder notation, I would say y such that it runs from -5 less than or equal to y this time, which is less than or equal to 3. So that's how you want to use set builder notation. Now you can see in exercise 3, the graph is kind of contained and it has very clear beginnings and endings, but that's not always the case. So if we look at this function right here, this is a quadratic function. And things to notice in a quadratic function is if we have arrows, that means that we are traveling all the way to the left, and then we are traveling all the way to the right. That means we can substitute any number we want in, and the graph will exist, and the graph will exist. So this is where you're going to look at this notation, and that really means all real numbers. Okay, it means every single number in the real set, and every single number in the set of real numbers. And then the y value here, you can see it goes up forever in the y value, but there's a minimum point right here. The graph does not go below this value -4, and it touches -4. So that's how you would express the range using interval notation. Okay, 2 more quick examples because we're going to be talking about this quite a bit here, right? Where this is the symbol for real numbers, by the way. Have you ever seen that? Okay, so sometimes functions run into problems, right? So for example, if I substitute 1 in this function, we can very clearly see that the output is -1. If I substitute 6 into this function, we can very clearly see that the output is 6.5. But when I substitute 4 into the function, my calculator gives me an error. And why is that? Well, if I think about it, 4 minus 4 is 0. And notice where that is in the function. It's on the denominator. We can't have 0 on the denominator. Okay? So you could say x does not equal +4 because it is undefined, right? And all other numbers work, okay, except for 4 because it is undefined. So that is called a restriction. Whoa, that's called a restriction on the domain, okay? That also happens when we're dealing with square roots. We have to be very careful when we're dealing with square roots. So for example, let's just try to substitute in 0 in this function. So I take y equals the square root of 0 plus 4. I get y equals square root of 4. I get y equals 2. So 0, 2 works. That works. We're looking for something that is not in the domain. Right? So if I try to substitute in -8, let's take a look at that. So if I've got y equals the square root of -8 plus 4, you're going to see y equals the square root of -4, and then that does not exist. This is a non-real solution. Okay, it's a non-real solution. Remember, 2 times 2 is 4. And then -2 times -2 is also +4, right? So that's going to give us a non-real solution. So that will also give you an error on your calculator, okay? All right, fam, good luck, and stop into office hours if you need any extra help.